Hello students, welcome back. Let us resume our discussion in section 2. Previously, we had some review in preparation. Now let's go to 2.3 and let's study images and preimages for group homomorphisms. Let G and G prime be groups. Let phi from G to G prime be a homomorphism. Then, its image and preimage preserve the group structure, the subgroup structure. What do you mean by that? If H is a subgroup of G, then phi of H is also a subgroup, but this time from G prime because phi is sending G to G prime. And we can go backwards too. If H prime is a subgroup of G prime, then its preimage is subgroup of G. So we have two parts and we have two proofs. First, for the image. So we know that this is a subgroup, so we have three properties to use. Number one, close under the group operation. Number two, there's the identity. Number three, the inverse. What we need to do is to establish the same thing for phi of H. So we have to prove that phi of H is closed. So X prime and Y prime belong to phi of H, then X prime times Y prime must belong to this image as well. That's what we have to do, the closed. And then the next, the identity. And then the inverse. Oh, member of G prime, so I need X prime there. Then X prime, X prime, X prime, inverse belong to phi of H. We have to prove these three. Close under the group operation in G prime, and then the identity in G prime, so we have E prime, and then the inverse. That's what we have to prove. And then what can we use? These X prime and Y prime belongs to the image set. So everything came from phi of something. So instead of those X prime and Y prime, you can rewrite like this. This one as phi of X, and this one as phi of Y, and then this one here is phi of X times phi of Y. So we can rewrite this one into that form. And then, let's see. This too came from, everything is in phi of E, so this should be written as phi of something too. And E prime is, okay, all right. I'll withhold that information. This one here can be rewritten like this. So it turns out this, and that can be written as this, and that using the idea of the image. Makes sense? Here, I didn't use that phi is an image, just any X prime, Y prime. Here, I used the fact that phi of H is indeed an image, so element here of this kind of form, so function value form. And as for this one, any idea? Any idea? Do you recall this? Oops, sorry about the typo. Do you recall this? And then as for this, do they ring any bell? I hope they do. Okay, here we go. We already established the identity inverse. Phi preserves the identity, so E prime is phi of E, so yes, E prime belongs to phi of H. So that one checks. And as for the inverse, phi of X inverse is actually phi of X inverse, and H is a subgroup, so it has inverse. So this belongs to capital H, so there you go. We already proved that phi preserves the identity in inverse, and this and then that are immediate consequences of those. So 2 down, 1 more to go. Now, how to prove the first one here? The image preserves the group operation. Well, that's what we have to prove. Yeah, but you can move it down to here. And then, can you see that phi of x times phi of y is, as a matter of fact, phi of x times y? Do you see that? And x times y should be back in H because H is a subgroup and it is closed under the operation in G. Do you see that? Well, that's the technique we are going to use here. We don't need this anymore. So choose any element, y1 and y2 from phi of H, and then they can be written in terms of the elements, phi of x1 form, phi of x2 form. Yeah, previously I used prime form, but this time different characters, but I hope you can understand all that. And then the multiplication y1, y2 is phi of x1 times phi of x2, but that can be combined into phi of x1, x2. You see, this belongs to capital H because capital H is a subgroup, closed under the group operation. So the product belongs to phi of H, the image. That completes the proof. You see, closed under the group operation. That's the reason why. So we have everything. So, image preserves the group operation. Image preserves the subgroup structure, excuse me. Preserving the group operation, that was the hardest part technically, but in any case, the conclusion is image preserves the subgroup structure. Okay, how about the next? The preimage. Let's see, what do you have to prove? Closed under the group operation. So if x prime and y prime belong to this, excuse me, x prime and y prime are members of primes, and preimage belongs to G, so I have to say x and y. X times y belong to preimage of H. Prime, excuse me, I forgot prime there. That's what you have to prove. And then the identity and the inverse. then X inverse belongs to so we need to prove these three. And then how did he define the preimage? We define like this. We didn't use inverse map. We use only forward map. F of this belongs to H prime. So if I apply that, this can be rewritten. Excuse me. Let me copy and paste that thing down here. Okay. So let's use this one, the easiest. Let's rewrite that. What do you mean by E belongs to O inverse image, the preimage? Sorry about a lot of typos here. Speaking and writing at the same time does that. So this can be rewritten as phi of E belongs to H prime. And can you prove that? And this one here I can rewrite as phi of X belongs to H prime, then phi of X inverse belongs to H prime. I can rewrite like this. This too, phi of X and also phi of Y belongs to H prime, then phi of xy belongs to H prime. You can rewrite like this. That observation here is more than halfway through. This is going to be easy, and that's going to be next easy, and that will be a little bit harder, but here we go. Ready? Okay, preimage. We have to prove these. First, the identity. Easy. Phi of E is E prime in H, so E is in preimage. I forgot prime here, excuse me, in simple typo to correct. Next, the inverse. X belongs to this, X inverse belongs to that, but that means phi of X belongs to H prime. And then that inverse belongs to H prime because H prime is subgroup. But then again, what is phi of X inverse? Phi preserves the inverse, so that's phi of X inverse. Phi of X inverse belongs to H prime, so X inverse belongs to the preimage. That completes the proof for the inverse. Make sense? From here to there, use the property that H prime is a subgroup. And here, we use the property that phi is a homomorphism, so it preserves the inverse. Third, the group operation, usually the hardest. x1, x2 belongs to preimage, and we want to prove multiplication belongs to that. But that means phi of x1 and phi of x2 belongs to H prime. Yeah, like this. And H prime is group, so multiply those and the product belongs to H prime. And then what do you do? Phi is a homomorphism, so group structure is preserved. So that's phi of x1, x2. That belongs to H prime, and consequently x1, x2 belongs to the preimage. That completes the proof, all three. So the conclusion, preimage also preserves the subgroup structure.